Hello, today we are going to talk about Conjecture 8 from our circle books. Conjecture 8 deals with inscribed angles in a circle. And this is a very important conjecture to talk about because many of the proofs for further conjectures will involve Conjecture 8 and inscribed angle properties. So if we take a look at the diagram here, we have angle CBD. This angle right here is what is called an inscribed angle. Right? So angle CBD is an inscribed angle. And all an inscribed angle is an angle whose vertex lies on the circle, whose vertex is a point on the circle. So notice here that point B, is a point on circle with a center A. So angle CBD or DBC is what is known as an inscribed angle. So upon further investigation, we can use GeoGebra to discover some different qualities or characteristics of inscribed angles. So here we're looking at this same exact diagram with some of the angle measurements provided from GeoGebra. So if we look at the measure of angle CBD, we have 53.54 degrees. Let's just call it 53.5 degrees. I have also used GeoGebra to find the measure of the central angle that angle CBD intercepts, and found that the measure of angle CAD, which coincidentally is the same measurement as this arc here highlighted in purple, all right, and I found that that was approximately 107 degrees. So what did this investigation provide us? Well, looking at these two measurements, it seems that the measure of the inscribed angle is going to be 1/2 of the measure of the arc it intercepts. So we can see here that 53.5 degrees is 1/2 of 107 degrees. And what this ultimately tells us is that the measure of an inscribed angle is going to be equal to 1/2 of the arc it intercepts, or 1/2 of the measure of the central angle. And this is an important discovery here. Right? So if the measure of an inscribed angle is 1/2 of the measure of an intercepted arc, right, this now paves the way for several other of the conjectures to follow. Right? But once again, all we have here is a discovery. Right? This isn't proof of anything. This only proves that it works in this one specific case. So in order to prove this conjecture too, we need to take a look at a separate diagram. So taking a look at the proof of this conjecture, we're going to need to alter this diagram a little bit, add a few things, and for simplicity and brevity's sake, I'm going to label a couple of the angles inside of the circle with numbers so that I won't have to spend the time listing out what the angles are. All right, so I'm going to first add this radii here that connects point H to the center E of the circle. I am also going to label this angle here, the central angle 3, right here, and I'm going to label this angle 1 and this angle 2. Okay, so those are the only additions I'm going to make to our diagram. This will help us speed things along in our proof. In order to do this proof, we are going to have to recall a few characteristics about triangles that we learned earlier this spring. The first of which involves the triangle sum conjecture as well as the remote exterior angle conjecture. So the first statement that we are going to use in our proof involves the remote exterior angle theorem, which is that the measure of angle 1 plus the measure of angle 2 is going to equal the measure of angle 3. So there we have step 1, which says that angle 1 plus angle 2 is going to equal angle 3. And we remember this because the exterior angle in a triangle is going to be equal to the sum of the remote interior angles. Okay, so here we have angle 2 and angle 1 are the remote interior angles, right? And then we have angle 3 over here. The next statement in our proof is a simple one, but it's really easy to overlook. Right? And that is that HE is going to be congruent to FE. And why is that the case? Well, looking at our diagram, we can see that both HE and FE are radii in our circle. So once again, because HE and FE are both radii, we can now say that they are congruent. So having two congruent sides in a triangle, what does that tell us? Well, that tells us that we are dealing with an isosceles triangle. And what do we know about the base angles in an isosceles triangle? We know that in an isosceles triangle, base angles are going to be congruent. Therefore, we can say that angle 1 and angle 2 are congruent. So because the base angles in an isosceles triangle are congruent, we can now say angles 1 and angle 2 are congruent. Okay, and what does that tell us? Well, we can go back to step 1 and see that angle 1 plus angle 2 equals angle 3. Well, if angle 1 and angle 2 are the same, we can now say that angle 1 plus angle 1 equals angle 3. And of course, our reason for saying that, we can use substitution. We can do some further arithmetic to say that angle 3 is going to be equal to 2 times the measure of angle 1. Right? And all that is simple arithmetic. So here we have the measure of angle 3 equaling twice the measure of angle 1. So where can we go from here? Well, what do we know about the measure of angle 3? What does that equal? Well, what type of angle is angle 3? Angle 3 is a central angle. What do we know about the measure of central angles? So we know that the measure of angle 3 is going to be equal to the measure of arc GH. And of course, we can say that because of the definition of central angle. So we have angle 3 is equal to arc GH. We also know that angle 3 is equal to twice the measure of angle 1. So now what can we say? Well, we can use substitution once again to say that the measure of arc GH is going to be equal to twice the measure of angle 1. And from there, we can do some more math and discover that the measure of arc GH, or I'm sorry, 1/2 the measure of arc GH is going to be equal to angle 1. So what does that even say? Right? We have this 8-step process here, and ultimately what we found is that 1/2 the arc GH is going to be equal to the measure of angle 1. Well, let's take a look at our diagram. What type of angle is angle 1? All right, we've talked about this earlier. We know that angle 1 is an inscribed angle that intercepts arc GH. Right? So if we were to look at this, if we were to highlight this whole piece here, right? We know that angle 1 is an inscribed angle. Right here we have angle 1. Right? It intercepts this arc right here, arc GH, and we've shown here that angle 1, or the measure of angle 1, is equal to 1/2 the arc GH, which is precisely what we wanted to show. Right? So here we've proven, in all cases, that the measure of an inscribed angle will be equal to 1/2 the measure of the arc it intercepts, or 1/2 of the central angle. So now that we've finally proven the inscribed angles conjecture, let's try an example. So let's take a look at this example right here. This is about as basic of an example as we can find. Okay, so here we have inscribed angle CBD again. Right here we have X symbolizing the measure of the inscribed angle. We have the angle that it intercepts, or I'm sorry, the arc that it intercepts at 72 degrees. So what do we know about angle X? Well, we know that angle X is going to be 1/2 the measure of the arc CD, which is 72 degrees, so X must be 36 degrees. And there's a basic example. Well, now that I've shown you an example, I've walked you through the proof of conjecture 8, how about you try a few examples on your own? So for this problem here, you will need to use what you know and what we've proven about inscribed angles in order to solve for X.